Okay, so we said in the previous video that the point form of Ohm's law gives a relationship between the electric field at any point inside the wire and the current density at that point. And the relationship is through the conductivity, and for a good conductor sigma is large, for a bad conductor sigma is low. How can we take this equation, point form of Ohm's law, and arrive at the form of Ohm's law that you know about from before? We know that J is current over area, and we know that delta V, the potential difference across a segment of wire, is electric field times the length. And so the point form of Ohm's law had in it J and E. So we can always replace the J and E by other quantities like I and delta V that will allow us to arrive at the other form of Ohm's law that you know about. So this is the point form of Ohm's law. If you replace J by current over area, and you replace the electric field by the potential difference across the ends of the wire divided by the length, then this will now get you the form of Ohm's law that you know about. Remember, it was that the delta V is equal to I times R. So if you look at this equation, can you fish out what the resistance is of the wire? If you write delta V as I times something, then this something turns out to be the length divided by sigma times the area. And so the resistance of the wire is the length over the sigma, the conductivity times the area. So this is the form of Ohm's law that you know about, and this is the way we can prove what the resistance is. And remember, current is not a vector. You'll always find in textbooks they put an arrow for the current, but remember, current is not a vector, it's a scalar. It could be positive, it could be negative, it could be zero. Current density J is the one that's a vector, and the current is equal to J dotted into the area for the case where J is uniform. In general, it's integration of J dot dA, but for this case where the J is the same everywhere, then it's just J dotted into the area. So the current is a scalar. J is the one that's a vector. So you have to make a proper choice of the area vector in order to get the current. So you have the J. J is determined by the electric field, because the electric field is proportional to J. Remember the point form of Ohm's law. So always J points in the same direction as the electric field. But depending the way you want to define the current, you have to choose the area vector to be either to the right in this case or to the left. If this is an open surface, you have complete choice to do that. So there's kind of a convention for that. We won't really bother too much about this, but I'm just mentioning it here to clarify the issue that current is not a vector. So when you put an arrow on the wire and you write the current I with an arrow, the current is not a vector. It doesn't have a vector nature. It's the current density that has a vector nature. Usually we can take the direction of the current to be in the direction of the J vector. So the units of resistance is ohms, and units, so ohms is volt per ampere gives you ohm. And usually they have tables that list all the materials and the corresponding value of the resistivity for those materials. The resistivity is just 1 over the conductivity. So it's just by definition, any material has a certain conductivity, and if you take 1 over the conductivity, this is called the resistivity. And you can list in tables the value of the conductivity or the resistivity. They'll be listed, and they give you the value at a particular temperature. And the reason for this is that this resistivity can change with temperature. So if you heat the wire, the resistivity will change. And we'll take this in a bit later to see how it changes exactly, and do some examples on that. So the resistivity is something that depends completely on the material being used, and it also depends on the temperature. For an ideal conductor, the resistivity is 0. For an ideal insulator, the resistivity is infinite. But resistance, it depends both on the material through the dependence on the resistivity, but it also depends on the geometry of the conductor, the resistor. It depends on the length and the area.